And we know that the student's expression must be incorrect because we need to identify two different mistakes that are present in the student's KSP expression. So the first mistake has to do with that phase of matter. So remember that the reaction quotient or the equilibrium constant expression does not include solids and pure liquids. And there is the reactant, calcium fluoride, which is a solid. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 7.1 to 7.4. As you can see on this slide, these topics fall under Unit 7 in the AP Chemistry curriculum, Equilibrium. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for Topic 7.1, Introduction to Equilibrium. Here are some essential knowledge statements from the AP Chemistry course and exam description. Many observable processes are reversible. Examples include evaporation and condensation of water, absorption and desorption of a gas, or dissolution and precipitation of a salt. Some important reversible chemical processes include the transfer of protons in acid-base reactions and the transfer of electrons in redox reactions. When equilibrium is reached, no observable changes occur in the system. Reactants and products are simultaneously present, and the concentrations or partial pressures of all species remain constant. The equilibrium state is dynamic. The forward and reverse processes continue to occur at equal rates, resulting in no net observable change. And graphs of concentration, partial pressure, or rate of reaction versus time for simple chemical reactions can be used to understand the establishment of chemical equilibrium. Now let's move on to the practice for Topic 7.1. This is question 1. In question 1, it says a sample of substance X2 is placed into an evacuated container at 400 Kelvin and allowed to undergo the reversible reaction represented by the equation shown above. The concentration of X2, the reactant, and X, the product, is measured over time, and the experimental data is shown in the table below. And so the question asks, based on the data, which of the following claims regarding equilibrium is most likely to be correct? So I will begin with choice A, which says, the system first reached equilibrium at a point between 10 minutes and 15 minutes, because that is the time period during which the concentrations of the reactant, X2, and the product, X, were equal. So this is a potential misconception that when students hear the word equilibrium, they think equal, but they think that somehow the concentration or the pressure of the reactants must be the same as the concentration or the pressure of the products. But equal concentration of reactants and products is not required to achieve equilibrium, so we can eliminate choice A. Now, moving on to choice B, it says that the system first reached equilibrium at a time period of 20 minutes, because at that point, the concentration of X, the product, is twice as much as the concentration of X2, the reactant, matching the stoichiometry of the balanced equation. Now, we do see that there is a 2-to-1 ratio of X to X2 in the balanced equation, but when a reaction reaches equilibrium, the ratio of the reactants and the products do not need to match the ratio of the coefficients. So we can eliminate choice B. And before I show you the details of choice C, I will remind you of one of those essential knowledge statements for topic 7.1. And it says that when equilibrium is reached, no observable changes occur in the system, reactants and products are simultaneously present, and then this part is described in the table in question 1. Concentrations or partial pressures of all species remain constant. So if you focus on the period of time where the concentration of reactant X2 remains constant, that would be from 30 minutes onward, and also the concentration of the product X remains constant. So the reason why the correct answer to question 1 is choice C is because that is the definition of equilibrium. The definition of equilibrium is when the concentrations or the partial pressures of all species remain constant over time, and in this table, that happens from a period of 30 minutes onward. All right, well, the answer to question 1 is choice C. Now, let's take a look at question 2. In question 2, we are given a balanced chemical equation, and it says that the substances Q2 and X2, which are the reactants, were placed in a rigid vessel and allowed to reach equilibrium according to the equation shown above. And the product of this reaction is QX2. Now, the graph below shows how the partial pressures of the reactants, Q2 and X2, and the product, QX2, in the system changed over time. Remember that in question 1, we noticed that when the concentrations or the partial pressures of all species remain constant, that is an indication that equilibrium has been achieved for the reaction. And so in this graph, we can't see any actual values or labels on the x-axis or the y-axis, but we can see that there are 3 horizontal lines that are located in this region that I'm highlighting on this slide. So that is an indication that equilibrium has been achieved because the system reaches equilibrium when the concentrations, or in this case, the partial pressures of all species remain constant. Now on the x-axis, we have a time labeled as T1. Equilibrium has not yet been achieved at time T1. But then we have another time labeled as T2, and so in that region, equilibrium has been achieved. Now here comes the question for question 2. It says, based on the graph, which of the following identifies the approximate time at which equilibrium was established and provides the correct justification? So we know that it's not going to be T1, it's going to be T2 as far as the location at which equilibrium has been achieved. Then we have to choose the correct justification. So it's not T1. I will eliminate choices A and B. And so with respect to choices C and D, so time T2, equilibrium has been established, is it that the rates of the forward and reverse reactions were equal, or is it that the rate of the formation of QX2 molecules was equal to the rate of disappearance of Q2 molecules? So the correct answer to question 2 is actually choice C, and I'll explain why choice D has an incorrect justification. So again, part of the definition of equilibrium is that not only do we have all of the concentrations or partial pressures remaining constant, the forward and reverse processes continue to occur at equal rates. So that is what choice C indicates for the justification, that the rate of the forward and reverse reactions are equal. So why is the justification in choice D incorrect? It has to do with the coefficients. So notice that we have coefficients from left to right of 1, 2, and 2. So focusing on the molecules of QX2, which is a product, and the molecules of Q2, one of the reactants, we can see that that is not a 1-to-1 ratio. So for every 1 Q2 molecule that is consumed, 2 molecules of QX2 are produced. So therefore, when equilibrium has been achieved, the rate of formation of substance QX2, the product, is actually twice as much as the rate of disappearance of substance Q2, one of the reactants. So that's why the justification in choice D is incorrect, and so the correct answer to question 2 is choice C. All right, now let's move on to the review for topic 7.2, direction of reversible reactions. Here are some essential knowledge statements from the AP Chemistry course and exam description. If the rate of the forward reaction is greater than the rate of the reverse reaction, then there is a net conversion from reactants to products, or you could also say from left to right. On the other hand, if the rate of the reverse reaction is greater than that of the forward reaction, then there is a net conversion of products to reactants, or you could say a net conversion from right to left. And then an equilibrium state is reached when the rate of the forward reaction is equal to the rate of the reverse reaction. All right, now let's move on to the practice for topic 7.2. This is question 3. In question 3, we are given a balanced chemical equation, and it says a chemical reaction occurs in a rigid vessel according to the equation shown above. The progress of the reaction is monitored over a certain period of time at constant temperature by measuring the partial pressures of the gases in the reaction vessel. The experimental data is shown in the table below. Now, based on our understanding of equilibrium, equilibrium would be achieved for this reaction when the partial pressures of all three substances remain constant over time. So I will highlight that region of the table. So we can see that from time t3 onward in this experiment, the partial pressures of all species remain constant. So the reactant AX has a partial pressure of 2.8 atmospheres, and that remains constant over time. And then the products, A and X, their pressures, 0.20 atmospheres, they remain constant over time from time t3 onward. So what happens during time t0 and t2, in that region, the system has not yet reached equilibrium. And according to the information in topic 7.2, between times t0 and t2, there is one of two possible situations. So we could have a net conversion from left to right, from reactants to products, and if that occurs, then the rate of the forward reaction is greater than the rate of the reverse reaction. On the other hand, there could be a net conversion from right to left, from products to reactants, and if that occurs, then the rate of the forward reaction is less than the rate of the reverse reaction. Let's analyze the details. In question 3, we are given the following question. Which of the following correctly compares the rate of the forward reaction with the rate of the reverse reaction between times t1 and t2 and provides the correct justification? So looking at the data for t1 and t2, let's focus on the reactant, which is substance AX. We can see that the partial pressure of substance AX changes from 2.6 atmospheres to 2.7 atmospheres. So that partial pressure is increasing. And then during that same time period, looking at the products, substances A and X, we can see that the partial pressure of each substance changes from 0.40 atmospheres to 0.30 atmospheres, so it decreases. Now, if the partial pressure of the reactant increases and the partial pressure of the products decreases, then there must be a net conversion from right to left. So there must be a net conversion from products to reactants between times t1 and t2, and so therefore the rate of the forward reaction is less than the rate of the reverse reaction. Now let's take a look at the 4 choices in question 3. So again, which of the following correctly compares the rate of the forward reaction with the rate of the reverse reaction? It's going to be either choice A or B. So in choices C and D, it says the rate of the forward reaction is greater than the rate of the reverse reaction, so that's incorrect. And now let's take a look at the justification to decide whether the correct answer to question 3 is choice A or choice B. Well, the correct justification is listed in choice B, that between times T1 and T2, the partial pressure of the reactant, AX, increases. That indicates that there is a net conversion from right to left from products to reactants, and the rate of the forward reaction is less than the rate of the reverse reaction. Now, if you're watching this video and you're wondering, well, why is the justification in choice A incorrect? It's because we're looking at a single time period. So comparing the partial pressure of a reactant, such as AX, with a product, such as substance A, at a single time point, that is not a valid justification for comparing the rates of the forward and reverse reactions. So what we really need to focus on is the change in the partial pressure of the reactants and the products. We're not simply comparing two partial pressures at a single point in time. We're looking for the change over that time period. So the correct answer to question 3 is choice B. And now let's move on to the review for topic 7.3, reaction quotient and equilibrium constant. Here are some essential knowledge statements from the AP Chemistry course and exam description. The reaction quotient, which has the symbol capital Q, describes the relative concentrations of the reaction species at any time, and that subscript C refers to concentrations. Now, for gas phase reactions, the reaction quotient may instead be written in terms of partial pressures, and we have capital Q with a subscript of P. So P for pressure, C for concentration. Now, the reaction quotient Q tends toward the equilibrium constant, which is symbolized with a capital K, such that at equilibrium, the value for the reaction quotient is equal to the value for the equilibrium constant. So when Q equals K, either in terms of concentrations or partial pressures, when Q equals K, the system is at equilibrium. Now, the next essential knowledge statement refers to two different equations or representations of Kc and Kp. So for the chemical equation that is listed with reactants A and B and products C and D, the equilibrium expression for Kc or Qc is written as follows. It is a ratio of the concentration of the products over the concentration of the reactants. These terms are multiplied together, and then there's also exponents that come from the coefficients in the balanced equation. So the representation of the equilibrium expression Kc is equal to the following. The concentration of the product C raised to the power of its coefficient times the concentration of product D, also raised to the power of its coefficient, and then divided by the product of the following. The concentration of substance A raised to the power of its coefficient times the concentration of substance B, again raised to the power of its coefficient. Now, when we switch from Kc to Kp, we switch from concentrations to partial pressures. So when a substance is inside a set of hard brackets, that represents the concentration or the molarity of those substances. And now for Kp, we have a term for partial pressure. That would be a capital P, so P for pressure, and then a subscript referring to the chemical formula of that particular substance. So the Kp expression would be written as follows. The partial pressure of product C raised to the power of its coefficient times the partial pressure of product D, again raised to the power of its coefficient, and then divided by the product of the following. The partial pressure of reactant A raised to the power of its coefficient times the partial pressure of reactant B, again raised to the power of its coefficient. And then the last essential knowledge statement for topic 7.3 is that the reaction quotient, Q, does not include substances whose concentrations or partial pressures are independent of the amount, such as for solids and pure liquids. Now that applies to both Q and K. What we're saying here is that in the expression for either the reaction quotient or the equilibrium constant, pure liquids and solids are not included in the equilibrium constant or the reaction quotient expression. Now, before I get to question 4 in this packet, I wanted to show you this is one of the pages of the AP Chemistry Equations and Constant sheet, and there is a section entitled Equilibrium. So if I give you a closer view of that section of the AP Chemistry equations and constant sheet, you can see that the expression for Kc in terms of molar concentrations and the expression for Kp in terms of partial pressures of the gases, that's listed there. All of the other equations that are listed in this section entitled equilibrium actually will be studied in Unit 8, which is entitled Acids and Bases. All right, now let's move on to the practice for topic 7.3. This is question 4. Question 4 asks, which of the following is the correct expression for the equilibrium constant Kp for the reaction represented by the balanced chemical equation shown above? Now, that Kp involves partial pressures, so we can eliminate choices A and B. When we see chemical formulas inside a set of hard brackets, that represents concentrations. But we are looking for partial pressures, so the correct answer is either choice C or D. Now, choice C, although it does have partial pressures, that expression in choice C is actually upside down. The expression should be products over reactants. So the correct answer to question 4 is choice D. And that would be that the Kp is equal to the partial pressure of the product N2O4 divided by the partial pressure of the reactant NO2 squared. And again, the exponent of 2 is referring to the coefficient for the NO2. So because NO2 has a coefficient of 2, the partial pressure of NO2 is raised to the power of its coefficient. So again, the correct answer to question 4 is choice D. Now let's take a look at question 5. In question 5, it says the dissolution of calcium fluoride is represented by the following equation. And we can see in the equation that is solid calcium fluoride, CaF2, is the reactant, and the products are the aqueous ions, calcium ions and fluoride ions. So I see Ca2 plus for the formula of the calcium ion, and I see F minus for the formula of the fluoride ion, and there is a coefficient of 2 for the fluoride ion. Now, the solubility product constant, the equilibrium expression, is Ksp, and we have that the student wrote the following expression for the solubility product constant Ksp, and this is what the student wrote. And we know that the student's expression must be incorrect because we need to identify 2 different mistakes that are present in the student's Ksp expression. So the first mistake has to do with that phase of matter. So remember that the reaction quotient or the equilibrium constant expression does not include solids and pure liquids. And there is the reactant calcium fluoride, which is a solid. So that is the first mistake. Solids and liquids are not included in the equilibrium expression, so mistake number 1 is the following. The student incorrectly included the concentration of calcium fluoride in the Ksp expression, but solids and liquids should not appear in the equilibrium expression. Now, the second mistake that the student made has to do with the chemical formulas for the products in this equation. So the formula for the calcium ion should be written as Ca2+. The formula for the fluoride ion should be written as F-, and we can see that these formulas in the student's expression are incorrect because of the missing charges on the ions. So mistake number 2 is that the student neglected to include the charges on the calcium ion and the fluoride ion. So the correct Ksp expression should be written as follows. The Ksp is equal to the concentration of the calcium ion, Ca2+, times the concentration of the fluoride ion, F-, and that should be raised to the second power. So the concentration of the fluoride ion is squared because the fluoride ion has a coefficient of 2 in the balanced equation. Now let's take a look at question 6. Question 6 says to write the expression for the reaction quotient, Qc, for the reaction represented by the balanced chemical equation shown above. So we will use chemical formulas inside hard brackets, but the only substance that will not be included in this Qc expression is the liquid, H2O. So with products over reactants, that would be concentration of HOBr times concentration of OH minus, and then divided by concentration of OBr minus. So this is the reaction quotient expression, QC. We have chemical formulas written inside hard brackets. Don't forget to include the charges on the ions in the chemical formulas. And there are no exponents because each substance has a coefficient of 1. All right, well, that's the answer to question 6. Now let's move on to the review for topic 7.4, calculating the equilibrium constant. Here is an essential knowledge statement from the AP Chemistry course and exam description. Equilibrium constants can be determined from experimental measurements of the concentrations or partial pressures of the reactants and products at equilibrium. And now let's move on to the practice for topic 7.4. This is question 7. In question 7, it says substance XY2 reacts with substance Y2 to produce substance XY3 according to the equation above. The table below shows the initial quantities of the substances present in a rigid 1-liter reaction vessel at 500 Kelvin. So we can see a table in which the initial amounts of all 3 substances are 5 moles of the substance XY2, which is one of the reactants, 5 moles of substance Y2, which is another one of the reactants, and then at the beginning of this experiment, before the reaction occurs, there is 0 moles of substance XY3, which is the product of this reaction. Now, after the system had reached equilibrium at 500 Kelvin, it was determined that 3.60 moles of substance XY3 was present in the reaction vessel. The value of the equilibrium constant, Kc, at 500 Kelvin is closest to which of the following? So what I will do to answer question 7 is I will use a strategy involving the formation of what I refer to as a RICE table. So the word RICE is an acronym, RICE, which stands for the words reaction, initial, change, and equilibrium. So in the first row of this RICE table, it is simply the balanced equation for the reaction. And then the next row of this RICE table refers to the initial amounts of all 3 substances present before any reaction occurs. Then the change row of this RICE table will refer to the changes in the amounts of the reactants and products as the system moves toward a state of equilibrium. And then the final row of this RICE table refers to the amounts of the reactants and the products that are present in the reaction vessel after the system has reached equilibrium. Now, we are told that the initial number of moles of substance XY2 is 5 moles. The initial number of moles of substance Y2 is also 5 moles, but we have 0 moles of the product XY3. Again, this is before the reaction occurs. Now what I'm going to do is fill in the change row of the RICE table, but since I don't know exactly what these values are, I will refer to the change in terms of an unknown quantity X. So take a look at the change row of the RICE table. I will write minus 2x, minus x, and plus 2x. Now I am using a minus sign to represent a decrease in the amount of the reactants XY2 and Y2. And I'm using a plus sign to show an increase in the amount of the product XY3. So minus for decrease and plus for increase. But if you're wondering why are those changes listed as 2x, x, and 2x, it's because the magnitude of the changes for the reactants and the products should be in proportion to the coefficients in the balanced chemical equation. And so in this balanced chemical equation, we have coefficients from left to right of 2, 1, and 2. And so that's why the magnitude of the changes are listed as 2x, x, and 2x. Again, minus to indicate a decrease in the quantity and a plus to indicate an increase in the quantity. Now, in this question, we are told that after the system had reached equilibrium at 500 Kelvin, it was determined that 3.60 moles of substance XY3 was present in the reaction vessel. So that is why I have written 3.60 moles for the quantity of XY3 present at equilibrium. Now, if 2x is equal to 3.6, then x would represent half of that quantity. So what is half of 3.6 would be 1.8. So take a look at the change row of this table in terms of actual numbers instead of x. So it's going to be plus 3.6, and 1.8 is half of 3.6, and then minus 3.6. So the change row of this rice table is minus 3.6, minus 1.8, indicating a decrease for the number of moles of the reactants, and plus 3.6 to indicate the increase in the number of moles of the product. Now what I will do is the math to determine the number of moles of the reactants that would be present in the reaction vessel after the system had reached equilibrium. So 5 minus 3.6 is equal to 1.4. So that means that there's 1.4 moles of substance XY2 present in the reaction vessel after the system had reached equilibrium. And 5 minus 1.8 is equal to 3.2. So I can see that there is 3.2 moles of substance Y2 present in the reaction vessel after the system had reached equilibrium. So now that my rice table is complete, I will read what we have to determine in question 7, which is that the value of the equilibrium constant Kc at 500 Kelvin is closest to which of the following. So what I will do next is to write the equilibrium constant expression based on this reaction. That would be products over reactants, and because it's a Kc, C for concentration, the Kc looks like the following. So products over reactants, the concentration of substance XY3 squared, because there is a coefficient of 2 for XY3 in the balanced equation. And then in the denominator of this Kc expression, you can see concentration of XY squared times concentration of Y2. Again, concentration raised to the power of its coefficient. Now, I had mentioned earlier that this is a 1 liter reaction vessel, and there is a difference between the number of moles and the molarity. So the number of moles is not necessarily the same as the molarity, but in this case, numerically, they are the same value. So the reason why they are the same value in this case is because moles divided by liters would be the number of moles divided by 1 liter. So looking at the final row of my rice table, 1.4 moles of substance XY2 divided by a volume of 1 liter, that gives me a molarity of 1.4 moles per liter. So similarly, we have 3.2 moles of substance XY2 divided by 1 liter for a concentration of 3.2 moles per liter, and then 3.6 moles divided by 1 liter, the concentration of substance XY3 at equilibrium is 3.6 moles per liter. Well, now that I have the concentration of all 3 substances in the reaction vessel at equilibrium, what I will do is pick up my calculator to do the math. So to calculate the value of the equilibrium constant expression, Kc, I will simply plug in the values for the equilibrium concentrations of each substance into my Kc expression. And so when I pick up my calculator, it will be 3.6 squared divided by the product of 1.4 squared times 3.2. Now, when I do this math, I will get the value of Kc at 500 Kelvin, and it works out to be 2.07 when I do that math. So I did create a rice table to help me answer this question, question 7, and the correct answer to question 7 is choice C. The value of Kc at 500 Kelvin is equal to 2.07. All right, now let's take a look at question 8. In question 8, it says that substance D2X2 decomposes according to the equation above. when pure D2X2 is injected into a rigid, previously evacuated flask at 350 Kelvin, the pressure in the flask is initially 3.00 atmospheres. After the reaction reaches equilibrium at 350 Kelvin, the total pressure in the flask is 3.75 atmospheres. And the value of the equilibrium constant, Kp, for the reaction at 350 Kelvin is closest to, and we see 4 numerical choices. So just like in question 7, we will use that same strategy to create a RICE table. So again, RICE stands for reaction, initial, change, and equilibrium. So there is our balanced chemical equation in the first row of the RICE table. And then initially, when pure D2X2 is injected into a rigid flask at 350 Kelvin, the pressure in the flask is 3.00 atmospheres. So that represents the initial value for the partial pressure of D2X2. And since D2, the product, and X2, the product, have not yet been formed before the reaction occurs, then the initial partial pressures of those two products would be 0. Now, in terms of the change, I will put the change in terms of x. So that would be minus x, and plus x. And as I had mentioned for question 7, the magnitude of the changes for the reactants and products should be proportional to the coefficients in the balanced chemical equation. And with coefficients of 1, 1, and 1, that's why the magnitude of the change would be x, x, and x. Again, minus to represent a decrease in the partial pressure of D2X2, and then plus to represent an increase in the partial pressures of D2 and X2. So in terms of x, when the system has reached equilibrium at a temperature of 350 Kelvin, the partial pressure of D2X2 in terms of x would be 3 minus x, and the partial pressure of each product would simply be x. Now, after the reaction reaches equilibrium at 350 Kelvin, the total pressure in the flask is 3.75 atmospheres. So 3.75 atmospheres represents the sum of the partial pressures of all 3 gases that are present in the reaction vessel at equilibrium. So the partial pressure of D2X2 plus the partial pressure of D2 plus the partial pressure of X2 is equal to 3.75 atmospheres. All we have to do now in order to solve for the value of x is set up a simple algebraic equation. So 3 minus x plus x represents the sum of the partial pressures, which is equal to 3.75 atmospheres. And if 3.75 is equal to 3 plus x, just based on simplifying that algebraic equation, that means that the numerical value of x is equal to 0.75. So what I will do now is simply fill in the number 0.75 for x. So the change row of my RICE table becomes minus 0.75, plus 0.75, and plus 0.75. And when I fill in the final row of my RICE table, the partial pressure of D2X2 when the system has reached equilibrium is 3 minus 0.75, or 2.25 atmospheres. And the partial pressure of each of the products, so D2 and X2, would be 0.75 atmospheres. Now let's go ahead and write the Kp expression. So the equilibrium constant expression, Kp, would be products over reactants, so partial pressure of D2 times partial pressure of X2 divided by the partial pressure of D2X2. And I have those values listed in the final row of my RICE table. So when I plug in the values for the equilibrium partial pressures of each substance into the Kp expression, the numerical value of Kp can be calculated as follows. 0.75 times 0.75 divided by 2.25. And when I do that calculation, I get a value of 0.25, which represents the numerical value of the equilibrium constant Kp for this reaction at 350 Kelvin. So the correct answer to question 8 is choice B, 0.25. So again, we made a rice table as a good strategy for answering question 8. Now let's take a look at question 9. In question 9, we are given a balanced chemical equation in which nitrogen monoxide, or NO, reacts with oxygen gas, O2, to produce nitrogen dioxide gas, or NO2. And the question says that equimolar amounts of NO and O2 are placed in a previously evacuated rigid reaction vessel where they react according to the equation above. And the partial pressures of the gases in the reaction vessel are monitored at constant temperature and recorded in the table below. Now, at what point during this experiment has the system reached a state of equilibrium? Well, that would be when the partial pressures of all three gases remain constant over time. And so if you look at the data in the table, you can see that from time T5 onward, the system has reached equilibrium. The partial pressures of all three species remain constant. And if we were to write the equilibrium constant expression in terms of partial pressure, so that is Kp as opposed to Kc, which would be concentration, the Kp expression would look like the following. Products over reactants, and in terms of partial pressure, that would be the partial pressure of NO2 squared, because NO2 has a coefficient of 2 in the balanced equation. And in the denominator of this Kp expression, it would be the product of the following. The partial pressure of NO squared, again, because NO has a coefficient of 2. And then also in the denominator, the partial pressure of oxygen, or O2. So there is my Kp expression. Let's go ahead and take a look at part A of question 9. And it says, write the expression for the equilibrium constant Kp for this reaction. So again, that would be products over reactants, and using the partial pressure of each substance raised to the power of its coefficient from the balanced chemical equation. Now, moving on to part B of this question. Use the data in the table shown above and your answer to part A to answer the following questions. So part I of part B says determine the value of the reaction quotient, Qp, at time T4. Now, why is it the reaction quotient as opposed to the equilibrium constant Kp? Well, at time T4, the system has not yet reached equilibrium. So this would be at time T4, we have pressures of 0.48, 0.74, and 0.52. So the partial pressure of NO is 0.48 atmospheres. The partial pressure of O2 is 0.74 atmospheres. And the partial pressure of NO2 is 0.52 atmospheres. So we're going to call this the reaction quotient Q, so Qp, and I will simply plug in the appropriate values in the appropriate positions. So pressure of NO2, 0.520. Pressure of NO, 0.480. Pressure of O2, 0.740. And when I pick up my calculator, the numerical value of the reaction quotient, Qp, at time T4 would be calculated as follows. 0.52 squared divided by 0.48 squared divided by 0.74. And when I do that math, I get 1.59. So that is the answer to part BI. Now, moving on to part BII, it says determine the value of the equilibrium constant, so Kp, when the reaction system has reached equilibrium, and that would be from time T5 onward. So my partial pressures are 0.420, 0.710, and 0.580. So the partial pressure of NO is 0.42 atmospheres. The partial pressure of O2 is 0.71 atmospheres. And the partial pressure of NO2 is 0.58 atmospheres. And this would be the system at equilibrium because the partial pressures are no longer changing over time at this point in the experiment. So a very similar set of calculations, except that we have a different set of numerical values. So partial pressure of NO2, 0.580, partial pressure of NO, 0.420, partial pressure of O2, 0.710. Now, when I pick up my calculator, it's going to be 0.58 squared divided by 0.42 squared divided by 0.71. And when I do that math, I get 2.69, and that represents the value of the equilibrium constant Kp when the reaction system has reached equilibrium. All right, well, those are the answers to question 9 in the packet. Now let's take a look at question 10. In question 10, it says, a chemist adds pure samples of substances A2 and Q2 to a previously evacuated rigid reaction vessel. A reaction occurs at 800 Kelvin according to the equation shown above. The partial pressures of substances A2, Q2, and AQ in the vessel are monitored over time as shown in the table below. Part A says that at time T1, the system reaches equilibrium. Determine the value of the equilibrium constant, Kp, for the reaction at 800 Kelvin. So we'll focus our attention on the Kp expression, which is in terms of partial pressures. So products over reactants, the partial pressure of AQ squared, because there is a coefficient of 2 for substance AQ in the equation, and then divided by the product of the partial pressure of A2 and the partial pressure of Q2. Now let's focus on time T1 in the data table, and we are told that the system reaches equilibrium, so the partial pressures of A2, Q2, and AQ represent the partial pressures when the system has reached equilibrium. So I will put the partial pressure of AQ in the numerator, and that would be 4 atmospheres. And I will put the partial pressure of A2 and Q2 in the denominator, and that would be 3.2 atmospheres and 2 atmospheres. And so now when I pick up my calculator to determine the value of the equilibrium constant Kp, the math involved is 4 squared divided by 3.2 divided by 2. And so when I do that math, I get 2.50 for the value of the equilibrium constant Kp for the reaction at 800 Kelvin. Now you will notice that at time T2 in this data table, the partial pressure of Q2 jumps up from 2 atmospheres to 5 atmospheres. So something must have happened in which most likely additional Q2 was added to the reaction vessel. Let's go ahead and take a look at part B of question 10. In part B, it says that at time T2, additional Q2 is injected into the reaction vessel, and the temperature of the reaction mixture is maintained at 800 Kelvin. A student makes the claim that equilibrium has been reestablished for the system at time T3. Do you agree or disagree with the student's claim? Justify your answer by comparing the value of the reaction quotient, Qp, with the value of the equilibrium constant determined in part A. So let's focus our attention on time T3 in the table. Let's go ahead and call this the reaction quotient, so not K, but Q. So Qp would be partial pressure of AQ squared divided by the product of the partial pressure of A2 times the partial pressure of Q2, and we will plug in the values for time T3 from the information in the data table. So that would be 5.28 for the partial pressure of AQ, 2.56 for the partial pressure of A2, and 4.36 for the partial pressure of Q2. Now, if, when I do this math on my calculator, I get a numerical value that is not equal to 2.50, which was my answer for Kp for part A, then I would say that the system has not yet reestablished equilibrium. On the other hand, if when I do this math, I get a value of 2.50, then I would conclude that, yes, equilibrium has been reestablished for the system at time t3. So when I do 5.28 squared divided by 2.56 divided by 4.36, this is what I get. Aha, 2.50 is in fact the value of Kp, which we have already determined in part A. So remember, from the essential knowledge statement for topic 7.3, the reaction quotient Q tends toward the equilibrium constant K such that at equilibrium, Q equals K. So if Q equals K, then we have established equilibrium. So I agree with the student's claim. At the time T3, based on the numerical data and the calculations, the value of the reaction quotient, 2.50, is equal to the value of the equilibrium constant, 2.50. So equilibrium has been reestablished for the system. All right, well, those are the answers to question 10. Now let's take a look at question 11 in the packet. In question 11, we are told that a pure sample of substance Dg is pumped into a previously evacuated rigid 1-liter container and allowed to attain the equilibrium shown above at 600 Kelvin. If 0.80 mole of substance D2 is present at equilibrium, how many moles of substance Dg were initially added to the container? Now, just like I had mentioned when we solved questions 7 and 8 in this packet, here in question 11, a good strategy is to create a so-called Rice table. So reaction, initial, change, and equilibrium. So the reaction row of the Rice table represents the balanced equation in which 2 moles of substance Dg decomposes to produce 1 mole of substance D2 and 1 mole of substance G2. Now, with respect to the initial amount of substance Dg that was added to the container, that's what we're trying to find. So we don't know the number of moles of Dg that were initially added to the container. However, we do know that substance Dg was in fact the only substance that was added initially to the reaction vessel. So that means that initially 0 moles of substances D2 and G2, the products, were present before the reaction occurs. Now, the 0.8 mole of substance D2 is present at equilibrium, and in terms of the change, remember that the magnitude of the changes for reactants and products should be proportional to the coefficients in the balanced chemical equation. And from left to right, we have coefficients of 2, 1, and 1. So the magnitude of change should be in that same proportion, 2x, x, and x. But you will notice that I wrote minus 2x because the amount of moles of substance Dg would be decreasing as the system moves toward establishing equilibrium, and the amount of moles of the products, D2 and G2, would be increasing. That's why it says minus 2x and plus x and plus x in the change row of my Rice table. Now, the ratio of D2 and G2 is 1 to 1, and you can see plus x and plus x. So therefore, we can assume that the number of moles of substance G2 present at equilibrium would also be equal to 0.80 moles. So the change for D2 and the change for G2 is plus 0.8. Now, since 2x is twice as much as x, then 2 times 0.8 would be 1.6. So I can fill in minus 1.6 for the change in the number of moles of substance Dg. Now, the next step in terms of solving and filling in this Rice table is I need to do a little bit of algebra that is related to the equilibrium constant expression. So the value of Kc is equal to 4.0, and I'm going to write concentrations instead of moles in the bottom row of my Rice table. So instead of writing 0.80 mole, I will write 0.80 moles per liter, or molarity. And that's because we have a 1 liter container, so I'm dividing the number of moles by 1 liter. So 0.80 molar are the concentrations of the products D2 and G2 at equilibrium. So here comes a little bit of algebra. This is my Kc expression, which is a Kc, not a Kp. That's why I have hard brackets to represent the concentration of D2 times the concentration of G2 divided by the concentration of Dg squared. Again, that concentration in the denominator of the Kc expression, that is squared because the Dg has a coefficient of 2 in the balanced equation. Now, when I fill in everything that I know at this point for equilibrium, that would be 0.80 times 0.80, again, the concentrations of the products at equilibrium, divided by the concentration of Dg squared, and I don't know that value at the moment, but that is equal to 4.0, the value of Kc that we were given in this question. So here comes the algebra. I'm going to rearrange this equation a little bit, and it would be concentration of Dg squared is equal to the following expression. 0.80 times 0.80 divided by 4. And when I do that math, I get 0.16, which represents the concentration of Dg squared. So the square root of 0.16 gives me 0.40. Now that number, 0.40, that represents the concentration of Dg present in the reaction vessel at equilibrium. So I will put 0.40 molar to complete the final row of my rice table. So now I know all 3 of the concentrations of the substances present in the reaction vessel at equilibrium. Now we have one more step to do to answer question 11. What number minus 1.6 is equal to 0.40? And that would be 2.0. So remember that 0.40 represents the number of moles of substance Dg that's present in the reaction vessel at equilibrium. So 2 minus 1.6 equals 0.4. So hopefully you can discover 2 things about question 11. The correct answer to question 11 is 2 moles of Dg were present initially in the container. So the correct answer to question 11 is choice D. And you can also discover that making or creating a rice table can be a very valuable strategy when you are solving equilibrium problems on the AP Chemistry exam. All right, well, since question 11 was the last question in this packet, we have now come to the part of the lesson where I give you advice to help you avoid common mistakes. My first piece of advice is if you are looking for additional practice problems related to topics 7.1 to 7.4, then you can review the information in my video for topics 7.1 to 7.5, and you can find that link in the video description area. My next piece of advice is what I normally say during this portion of the lesson. Read the question carefully and make sure you are answering the question that is being asked. Always show your work for your calculations, and when setting up a calculation that involves substituting numerical values into the reaction quotient expression, Q, or the equilibrium constant expression, K, take care to avoid errors with arithmetic or algebraic manipulations. Equilibrium is reached when the concentrations or partial pressures of each substance involved in the reaction remain constant. At equilibrium, the concentration of the reactants will not necessarily be the same as the concentration of the products. At equilibrium, the rate of the forward reaction is equal to the rate of the reverse reaction. The relative rates of change for 2 different substances involved in a chemical reaction are determined by the stoichiometry, that is, the coefficients in the balanced chemical equation. At equilibrium, there are no observable changes in the system. However, the substances involved in the reaction have not stopped reacting or colliding with each other. Equilibrium is a dynamic process that involves the simultaneous conversion from reactants to products and vice versa. Suppose you are given a graph of experimental data showing how the concentrations or partial pressures of the reactants and products are changing versus time. You will notice that equilibrium is reached when the data shows horizontal lines indicating that the concentrations or partial pressures of the reactants and products remain constant versus time. And now just a few comments about vapor pressure. The vapor pressure of a liquid is a property that was mentioned during topic 3.2, properties of solids. The vapor pressure can be measured in a sealed container of liquid at constant temperature. The vapor pressure is constant at a particular temperature because a reversible process occurs in which the rate of evaporation is equal to the rate of condensation. The vapor pressure of a liquid depends only on the temperature of that liquid. Vapor pressure is not affected by the container volume, the shape of the container, the liquid volume, or the surface area of the liquid. If the rate of the forward reaction is not the same as the rate of the reverse reaction, then there will be a net conversion from reactants to products or vice versa. So if the rate of the forward reaction occurs at a faster rate, then there will be a net conversion from reactants to products, from left to right. On the other hand, if the rate of the reverse reaction occurs at a faster rate, there will be a net conversion from products to reactants, or from right to left. The following tables show the variety of mistakes that students tend to make when they write the equilibrium constant expression. So I'm showing you all of these student mistakes to make sure that you recognize them, and then you avoid making those mistakes when you take the AP Chemistry exam. In this equation, we have solid magnesium hydroxide as the reactant on the left, and then on the right side of the equation, we have the aqueous ions, magnesium and hydroxide. Notice that there is a 2 in front of the hydroxide as a coefficient. So the correct equilibrium constant expression for this reaction is known as the solubility product constant, or KSP. And you can see that we're using hard brackets to indicate the concentration of the particles. And notice that there is no denominator. And that's because the magnesium hydroxide is a solid, so pure liquids and solids are not included in the equilibrium constant expression. So the correct way to write the KSP for this reaction is concentration of magnesium. Notice that we have the charge of Mg2+ inside hard brackets, and then times the concentration of the hydroxide ion squared. Now I will show you several examples of student mistakes respective to this particular equation. So here's the first mistake. Including a solid or a liquid in the K expression is an example of a student mistake. The next example of a student mistake is neglecting to use the coefficients from the balanced equation as exponents in the expression for the equilibrium constant. Another mistake that students make is instead of using hard brackets to indicate the concentration, they use parentheses. Another example of a student mistake is they write Mg and OH, but they omitted the charges on the ions in their equilibrium constant expression. Another mistake is to include the coefficient in the formula, and that's written inside the bracket. So that's an example of a mistake. And then one more example of a mistake for this equation is that students will place the exponent inside the bracket instead of outside. Now I will show you another chemical equation. Now this one involves CH3OH as the reactant, and then the two products are CO and H2. You will also see a coefficient of 2 with the hydrogen, H2, and these are all gases. So I will show you the correct expression for not the Kc, but rather the Kp. So in this case, I have the partial pressure of CO times the partial pressure of H2, and that's squared because of that coefficient of 2 in the equation, and then divided by the partial pressure of CH3OH. Now that you see the correct expression for Kp, let me show you several examples of student mistakes. Now the first one is actually kind of subtle, and you might not recognize the mistake, but take a look at what the student wrote. they did not write Kp equals. So omitting the K equals as part of the expression at the beginning is an example of a student mistake. Another example of a student mistake is to accidentally write it upside down. So instead of writing products over reactants, this student flipped the expression upside down. Another student mistake that can be made on the AP Chemistry exam is, again, as I mentioned earlier, neglecting to use the coefficients as exponents. Another mistake is to not recognize the difference between Kp and Kc. So what this student did is they wrote hard brackets, but this was for a Kp expression, so that's incorrect. So again, know the difference between Kp involving partial pressures and Kc involving concentrations with hard brackets. Now, this student did not write hard brackets, they wrote parentheses, but there is no capital P for pressure. So another mistake is omitting the capital P symbol, which indicates partial pressure when you're writing a Kp expression. And then this student accidentally put a plus sign in between those two terms in the numerator. Now, that is incorrect because the mathematical operation is multiplication. So the fact that a plus sign is visible makes it look like those two terms are being added together, and that's incorrect. And then finally, another example of a student mistake that students can make is they jump to the calculation part. And if the question says, write the equilibrium constant expression, then we don't want to see simply a setup for a calculation. You should write the expression. So I've shown you examples of the correct way to write a Kc or a Kp, and I've shown you several examples of student mistakes with the hope that you will recognize those mistakes and then avoid making them when you take the AP Chemistry exam. All right, just some final pieces of advice for you before we end this lesson. Setting up a RICE table, and again, RICE is an acronym for reaction, initial, change, and equilibrium. Setting up a RICE table is a helpful strategy to keep track of the changes that occur in the amounts, moles, the concentrations, or the partial pressures of reactants and products as a chemical reaction occurs, moving toward a state of equilibrium. And with respect to the change row of the RICE table, remember that the magnitude of the changes for reactants and products should be proportional to the coefficients in the balanced chemical equation. Changing the temperature will change the value of the equilibrium constant K. And then finally, it is possible that different sets of numerical values, when plugged into the equilibrium constant expression, will produce the same calculated value for the equilibrium constant K. So there is not a unique set of numbers that will lead to the numerical value of K. Different sets of numerical values will achieve equilibrium and therefore be equal to the value of the equilibrium constant. So now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 7.5 to 7.8. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.